Hi, everyone. Welcome back to F110 Autonomous Racing. This lecture is going to continue our previous discussion based on SLAM, or simultaneous localization and mapping. And previously, we spent a lot of time looking at the mapping portion of SLAM. And in today's lecture, we are going to mostly talk about localization. And in particular, I'm going to describe a very popular and a good method of doing localization for a mobile robot called particle filters. And that's what we also use for our autonomous race car. So let's just jump right into it and discuss how does localization work and what are particle filters and why they are so famous and useful. Okay, let me just switch to a laser pointer. All right, so the setting of the problem is the following. So previously, we spent a lot of time discussing that if you had a robot and the only data source on that robot was a 2D scanner or a LiDAR type sensor, then you could use scan matching along with Bayes' rule to build this knowledge of the surrounding itself, or build a map of the surrounding. And in particular, we discussed the principle of using occupancy grid mapping. And I hope you all recall that. If not, then I encourage you to go back and watch just the previous video. And so here we are solving a dual or sort of a separate problem, right? So in the previous setting, when we were doing all this occupancy grid mapping, I even recall specifically stating that that only works if you know where the robot's location is, right? So you are getting data in the frame of reference of your sensor, but you want to transcribe or develop the map in the frame of reference of the world. And that rigid body transformation only works if you know where the base link of your autonomous race car or your robot is. So that was a very big assumption. Today, I'm going to talk a bit about how do you actually do that, right? So our problem setting is the following. Here, we are already given a map. So we are given a 2D style occupancy grid map because our problem is mostly 2D. We are given autonomous race car, the F1tenth race car, if you will. And in that race car, we have a 2D Hokuyo scanner type LiDAR, which will give us range measurements to the surroundings of the obstacles. And then we can also assume that we have some source of odometry, or odometry is just saying that if we have a history of how our robot has moved in the world, right? It could come from inertial measurement units or wheel encoders. And if you recall, previously we have spent an entire lecture discussing dead reckoning and other odometry techniques. So given these three things, the problem is, can we figure out where we are in the world, or where is the car located precisely in the map? So you can see it's a different problem than mapping, because in mapping, you are trying to learn what the world looks like by populating these occupancy grid cells. Here, we are saying in a previous iteration, you would have already developed the map, or someone kind enough has given the map to you. The problem is your car is now placed in the map. It's a racetrack, for instance, and you want the car to follow a certain line. Well, for that to take place, you have to first figure out where you are in the map to begin with, and how can you keep track of your own position in a known world. And that's the problem setting of localization. Okay, so our goal is to figure out the pose of the robot inside a map, where we all know that pose is given in the 2D problem with the XY position and the orientation theta of the robot. So with this problem setting, let me first show you what this would look like. So here you can see we have a pre-built map. And the car that you see on the top left is autonomously navigating in this environment, which was previously, mapped with this 2D occupancy grid. And so here, what you see is, the green arrow is what the output of localization looks like, right? So we are guessing with some probability or very high likelihood where we are in the world. And all these red arrows that you see are what are termed as particles. And so it's not clear right now because we haven't really discussed what particles are. But by the end of this lecture, you'll basically understand what you just saw in this sort of a snippet of a video of autonomous navigation in this environment by the 1/10 car. All right, so how do we go about building this map? Well, we need, sorry, not building a map. How do we go about doing localization? So what we need are some key ingredients that will allow us to localize our car. So let's go over sort of what is required, or let's formalize the problem a little bit more. So the first thing you need are laser scans from your LiDAR on top of the vehicle, and that might look something like what is shown on the screen right here. Another thing you need is what I was describing as odometry. So you need odom data, which can be thought of as what are the previous control inputs that can help me figure out how my car has moved in the world, right? So I need to know, what control commands, for instance, were given to the car for it to move and for how long, which direction, all that good stuff falls under odometry and control input. And finally, localization has to be done within a context of an existing map. So we assume that we have a 2D occupancy grid map, sort of what is shown in your head on the screen. And so this is the input to the problem. I have data from my vehicle. I have a history of control inputs, or a stream of control inputs. And then I have access to a prior map within which I'm trying to localize. So given all these inputs, the output of localization is going to be your best guess of where you think you are in the map, which is your best pose estimate. And this is, while this is the only output that you expect and you are sort of interested in obtaining out of the localization method, but underneath the hood, especially in terms of particle filters, you get this pose estimate by analyzing something called particles, and I'm going to describe you in detail how that works in this video. So this lecture is going to cover a specific algorithm for localization. There's many ways to localize, goes without saying. But for F110, what has worked really well, given that we have a LiDAR and a 2D occupancy map, is particle filter. So we are going to understand this algorithm intuitively and a little bit of math, but nothing too complicated beyond Bayes' rule. And then I'm going to talk a little bit about the ROS side of things. How is this implemented in ROS? What are things you can tune when you implement a particle filter? Our simulator also supports a particle filter, which can be GPU enabled. And then finally, we'll wrap up by pointing you towards some more detailed resources, because localization is just one of the things in this broad area of probabilistic robotics. And so I want you to point you towards the correct sort of resources in that space. All right, so let's talk about what is particle filter localization. I hope the setting of the localization problem, at least in terms of the inputs and outputs, is clear. So once again, not surprisingly though, we go back to this idea of Bayes filtering, which we spent actually a lot of time talking about in our SLAM video or the lecture. And the key idea, if you don't recall, in Bayes' theorem is that you want to update what is called the posterior, and posterior is sometimes called belief. So you want to update the posterior of the thing that you're trying to estimate by merging together your previous belief about the same thing that you're trying to estimate and adding new information that is provided by your sensor measurements, right? So this is how we also updated the likelihood or the log odds of every cell, if you remember in the SLAM. So in the terms of localization, you can think of a very high level problem that we want to estimate, or we want to update the posterior or maintain our belief of the pose of my robot. So x of t in this equation refers to not the x coordinate, but the entire robot state or the entire robot pose at time t. And you want to figure out how can this belief or your estimate of the pose or the state of the robot evolves, given that you know the previous state and you know all the history of the data from the previous time as well, right? So from 0 to t basically. So given your previous state and some observations from previous steps as well, or at least from the previous immediate one step, you want to figure out what is your new robot state. And these are again being described in very generic terms. So there are several questions arises. It's not immediately clear how actually this accomplishes the task of localization. So let's distill this high level idea further. And the way we can think about this is by trying to attempt to answer these questions listed on this slide. So the first is, how do you represent the robot state in the localization problem? I think this is the easiest answer of all. The state, as I've already said, in our case is going to be the pose of the robot. So pose of the robot, it's the 2D coordinates plus the orientation. And that's what is the interested, the thing of interest for us, which we can describe as a robot state. Then you may want to know, how do you represent this probability, right? This seems to be the key towards getting any posterior or belief established. We need to sort of decompose this complicated function. This function is the likelihood of being in a certain state conditioned upon the data you have observed in the past, right? So think about that statement for a bit, and it'll become clear as to why this is necessary for estimating future states. And then finally, we want to think of, what does this data look like, especially in the context of our F1tenth vehicle, right? So is this some LiDAR data? Is that enough? Or do we need some other sort of special sensor to be able to estimate this probability? So let's try to answer all these questions. So let's begin by looking at the data in the F1tenth car. So for mobile robots in general, and that's true for our F1tenth vehicle as well, we can partition the historical data or data that we are using to estimate the state of our robot into two broad categories. The first is your perception data, or what is being described as perpetual data in this slide. So your perception data is, for instance, the laser range measurements that are being produced by the LiDAR sensor on your robot. And the second category is odometry data, or the history of actions or the control inputs that have been logged and that can give you some indication of how the robot has moved in the world. So you can sort of separate out the generic data which was present in the previous equation specifically into perceptual observations at time t, so the data from your LiDAR sensor, and a history of the previous action at the time t minus 1, and you'll go back all the way to time 0. Okay, so to recap, we need to calculate the posterior or the belief or the updated state. State is a proxy for just the pose in this case. We want to update our estimation of the pose or the probability of being in a certain pose, given that we know where we were and what data is the robot reporting right now and what actions did we take in the past. So mathematically speaking, I'm not going to show you all the steps because I think it's best that that's a slow process to understand how that previous equation has been expanded out into this expression. But we can write, let's understand this equation. We can write the previous equation as a product of many different terms, and it's best that we read this term going from the actually from the right hand side to the left rather than the left to right. So we begin by stating that we have a previous estimate of where we think we are in the world, and that's called your previous belief, and sometimes it's simply called a prior. So you have a prior on where you were in the world or in the map, and so one can ask, like, where does this come from? So the very first prior might have to be provided by the user, right? So there's actually a guess by the user that this is where I think the robot is kept in the world. But the nature of this equation, if you notice, is that the new estimate depends upon your prior. So that's why there is this recursion involved in solving this estimate. But that's a separate thing that we will describe in more detail in just a bit. Going back to this sort of expression, we have a prior belief of where we are in the world. Then we have some data on what actions did we take, or how did the robot move from its prior location. And we use that to update our belief, basically, by multiplying our likelihood of being in a certain position based on the actions that we just took, and based on where we were in the previous time step. And so this probability is what is being called the motion model. And then you can include, if say your motion model is that you drove straight for 2 meters, in your probability, you may want to include some noise, right? So it's 2 meters plus some uncertainty, because there's always some sensor measurement noise and estimation noise. But the idea is that what we are trying to compute is update our belief of where we were at time t-1 with the knowledge of how the robot has moved in the world. Kind of similar to odometry and dead reckoning. But then comes the part where we get to observe some data from the robot. And then you can pose the question, well, how likely am I to see what I'm seeing with the LiDAR scans, assuming I am at some pose x of t? So this is what is called the sensor model, which, as indicated, is showing you we are computing how likely your measurements are given where you think you have been, or where you think you are now as a result of this belief update. And so you want to conduct this update over all possible beliefs. And so once you have all these products, your new belief also needs to behave like a probability. So we normalize it so everything adds up to 1, and the right hand side, the entire left hand side expression is computed to as a probability as well. Okay, so the whole idea is that these representations of these probabilities are going to be non-parametric. If that's not clear what that means, I'll just explain that through an example. But non-parametric means that we are going to only be dealing with some finite samples, right? So remember, there's an integration here where you are updating your belief based on sort of all possible locations of where you could have been. And so all possible locations could be infinite. So we just sample them out. And in practice, we just basically are doing a finite approximation of this continuous integral. And we do so by using particles. And I assure you that if the mathematical sort of details were high level and not clear, they will become clear when we see an example of the particle filter. But in any case, I will share with you details of where this expression has been derived from. So let's actually look at an example first. So here is the initialization of my sort of a problem setting. I am given a 2D cost map. In this case, let's assume that we are given, this is some part of the map that was built using the cartographer algorithm that we discussed previously, or even HectorSlam. And it honestly doesn't matter how you generated the map. But just so that we are all on the same page, the black portions or the darkest pixels in this occupancy grid, they represent the boundaries where you got, an obstacle is present or they are occupied. The lightest gray represent free cells or non-occupied. And then some of these gray cells are unexplored, obviously. So by the way, since we're not doing mapping anymore, these unexplored cells don't play a role, okay? The idea is we want to localize within this known map of the world. So the way we do it is we first need the initial guess of where we think we are in the world, right? So this can be through odometry, or a user can supply, the location, like for the, just for completeness sake, in the context of autonomous racing, this is likely to be the start-finish line, or somewhere on the start-finish line, right? So the idea so this red arrow, as is indicated, this is our initial guess on the pose of the robot, pose being where it's located and the direction in which it faces as well. And our job is that as this robot moves in the world, we want to keep maintaining some guesses of the latest pose of the robot. So here's the idea of particle filters in a nutshell before I go into the example. The idea is particles are just a fancy term for saying that we are making guesses about where we think we are. So in the localization problem, what you are seeing on the screen, every particle is a possible guess of a pose of a robot. And it's a random guess as well to begin with, right? So you give me an initial pose by the user. I can assume that the real location of the vehicle is somewhere in the vicinity of where you think it was when you initially placed the car, because you didn't bother to take all possible measurements, or you didn't have the exact wheel marked out on some X marks the spot on the floor to make sure the car is always kept at the same point. So you gave me a rough idea, so that's fine for me to assume that the real position of the robot would be somewhere in the vicinity of that initial guess. And so each of my guess is what is called a particle, okay? And you will see in a bit why they are called particles as well. But for now, that's what we assume. We assume that each particle, that you give me a guess, and I assume a Gaussian distribution around your initial guess, and then I randomly sample possible values of the poses from that distribution. So why do we do this though, is the question, which has not been answered yet. So let's keep going ahead with that example, and slowly we'll get to every aspect of particle filters. So we have this initial guess, and things become more interesting when you take robot motion into account. So our robot moves in the world, which is, you know, this sort of cyan arrow on your screen. And based on that, you are applying this measurement of the control input or the motion model with the possible poses as well. Okay, so as your robot moves, you also update the set of possibilities of your robot's pose. In other words, you take the particles and you apply a motion model to get new particles as well. So I think a question which arises is, why do we have so many guesses? What good comes of assuming that you have thousands of guesses of particles? Don't we just need one guess? And the short answer is yes, we actually just need one estimate at the end of the day. But you will see now why doing this randomized local guessing of particles is going to lend itself towards finding that one answer. Okay, so we have this problem that we don't know exactly where the robot is, so we are just randomly guessing with some assumed distribution that these are possible poses of the robot. So now I'm going to hone in on just one particular particle and tell you why or what purpose it serves, right? So this is a bit exaggerated. A particle has been sort of blown up with its position. But the idea is that for each particle, since we already know the boundaries of the map, we can compute that if this hypothetical location was close to the true location of the car, or assuming that the car indeed matches the pose of this random particle, this is sort of the range data that I should be seeing. Okay, so let that thought settle in for a second. The idea is I'm assuming a random pose by taking into account the previous motion and the initial pose and all that stuff, but still it is random. And what I'm saying then is, looking at where I am on the map is known, remember, right? This is not a mapping problem. So given my random pose, what should I expect to see as a laser scan if this was actually where my car is? That's what each particle is trying to figure out. And so in more sort of formal terms, we can raycast or do some fake laser scan. The fake laser scan means we are not simulating a LiDAR on every particle. What we are doing this raycasting to figure out what kind of range measurements would we expect to see if this particle represented the true pose of the car. And so you know, your question can be that, well, how hard is it creating this sort of a approximation compared to the model update? The model update is keeping track of actions. And then, you know, you may want to know what is the exact model that we use for raycasting as well, because a lot of the evaluation of whether this particle is any good or not will depend upon these assumptions. So I won't go into too much details except giving you a high-level intuition. This step is usually the hardest step in any particle filter algorithm, right? To figure out what you would have seen if you were in this position, or if this particle represented the true pose. While it is complicated, you know, based on a raycasting model like the one shown here, it's very, very simplistic and straightforward. There are more complicated ways to model the sensor information and raycasting as well. And that's, again, a bit out of the scope for what we want to really get through to today. But I just want you to be aware that ray tracing or raycasting has also evolved. We just don't always deal with these parallel rays of light. You can have more realistic models too. But let's go back to the idea of how do we evaluate whether this is a good candidate for the real pose of the robot or not. So remember, the pink sort of rays or the pink distances are range measurements that you would expect to see, because you know the boundaries of the map, if your car was at the pink particle. Now, we don't know where the car is, right? So we don't know really where the green dot is, assuming the green dot represents the car. But what we do know is the range measurements being reported by the LiDAR on the real car. So you have true range measurements, which you are seeing from your sensor, and then you have this fake ray measurements or ray casting distances ranges that you are speculating you would have seen if this particle was good, or if this pose was a good estimate. And so I hope you can guess almost what the next step is. We have the ground truth of what ranges we see. The problem with that is we don't know where we are. And then we have an estimate of what ranges would we expect to see given we assume some random pose. So to evaluate whether your random particle or that random pose is any good or not, we just have to measure how close are these two range estimates to each other. While both of them are not estimates, how close is your range estimate to the ground truth range that you see? So you can compute a score or a correlation between the set of ranges that you would see from a particle and with real data that you see. And this correlation can be thought of as a weight or a weighted measurement of the particle. So in other words, let's simplify things a bit, at least pictorially. You have this one possible particle out of 1,000. And what you say is that if this was the pose of the car, this is what would I have expected to see as the LiDAR scan. And then you have a correlation between what you expect the LiDAR scan to be and, you know, in this case, what the shape of the map is. But you can have a correlation between your fake LiDAR and your real LiDAR scan. And so with enough guesses, you know, you can have another guess like so on and so forth. So you're always guessing what would I expect to see versus what my LiDAR is reporting, with the idea that somewhere in that random guess would be at least one or a few particles which have a very good correlation between the fake sort of raycasting and the real LiDAR scan. Or in this case, this particular particle reports that it sees the orange data, which actually fits very well the map boundaries of our 2D occupancy grid. That's why particle 6 in this case has the highest correlation. Therefore, we give it more weightage. And I haven't explained how these weights are actually incorporated, but remember that the Bayesian estimate of the pose was a recursive equation. So the way that plays a factor in all of this mechanics is that you are not done if you find the particle with the highest weight. You can't just say this is my best guess and everybody goes home. The problem with that is because one can say, well, you got lucky because you randomly initiated these particles. So what if you get unlucky and you don't initiate a particle which has a best correlation with your real data? And so for this reason is where we have the recursive nature of a particle filter. We will use the weights to play with the importance each of the particle gets in the next stage as part of the belief. So particles with high weight contribute more to your prior belief than particles with low weight. In much simpler terms, since each particle anyways is a sample, you are likely to sample more poses near the locations with particles which had higher weights. And so if you do this recursion enough times, you can have some sort of a stopping criteria where the correlation doesn't change significantly enough. But when you do this enough times, you can then be certain that when you do this resampling, you are left with the most dominant particles, or the particles which are most likely to represent the true pose of the car. Okay, so that was sort of the high level intuition behind particle filters. It really is not that complicated. I just wanted to break it down into every single step, which is why, it might seem it's too many steps. It's really not. It's pretty fast as well, but there are some computational bottlenecks that we will talk about. Okay, so in ROS, this method that I just described is called adaptive Monte Carlo localization. This is a dedicated package called AMCL in ROS that can be used for localizing a robot moving in an occupancy 2D grid map. This is actually a snippet of this Monte Carlo localization algorithm. So you can see our basic equation is we have initial particles that we want to use to update our pose. So we get some odometry data, which is our motion model. We get the latest sensor readings, which is going to be used to look at the correlation between fake scans and real scans. And then given a previous state and a previous action pair and a previous observation. So remember how we had, we had partitioned the data into the perpetual observation or the perception part and the odometry part. All these routines are going to compute that basically product of the expression, the big probabilistic expression in terms of the particles. And then they will also return basically the best guess of where you think you are in terms of the locations of the particles. So your inferred pose is the expected value over the distribution of the particles. Okay, so if there were no resampling, by the way, right? So if you had, let's say, 1,000 particles and you only wanted to have a combined sort of a expected value, it would be no good because of the fact that you have maybe uniformly sampling in the first place. So even though some particles have higher weights than the others, they may still be very far spread out, pretty far out from each other to give you a precise estimate from where you are. So instead, what we do is, like I said, we take the correlation weight corresponding to each particle into consideration, and we use that weight to kind of sample in a non-uniform manner or proportional to the weight of the particle, so that we have a better chance or a better shot at finding a random particle which actually aligns very, very closely with where the robot is. So in other words, instead of a uniform sampling, resampling gives you these peaks in your distribution of particles. So you tend to have clusters of particles which are more packed together because previous sort of the weights of these locations were very high because of the correlation of between the fake data and the real data from the LiDAR. And so after a lot of iterations, you will find these pockets, and this allows you to do even further resampling, right? So in the next step, we would resample just within these clusters. And so if we do this enough times in an iterative manner, we are bound to left with only a few particles, at which point you can either just greedily choose the particle with the most correlation, or you can do expectation over the set of remaining particles. Okay, so here's a toy example to show what's going on. So what you see is actually a bit hard to see, but the blue line, which is barely visible, is the real ground truth of this simulation. Now, the thing which is simple about this example is that we don't have a 2D occupancy grid. Our map is just these 4 star features, right? So these 4 locations which don't move can be thought of as a map, a very rudimentary map. The red line is the estimation of the pose of this robot based on particle filter. So each of the particles is trying to compute how well is the fake distance from each of these features similar to the true distance reported by the robot. And you see this black line, which is non-circular. This is the odometry. If this is the pose of the robot, if you were only using dead reckoning. So it has some drift, right? Because we have seen how IMU or dead reckoning alone is not enough for precise localization, because there is no way to have any kind of feedback, or you can't close the loop and reduce your uncertainty as there is no external measurement. You are just assuming how you are drifting in the world based on previous commands and some behavior of the robot. So in the simple example with the map being just these 4 features, I think it makes the point clear how particle filters behave, and the simplicity of this map also is one of the reasons to show how raycasting is not that big of an assumption. It works in most settings, Now, of course, here you only have 4 rays to simulate, or not even 4, you only have those rays to simulate which are within the field of view of your LiDAR sensor. But the same thing applies to an actual LiDAR, and you will see in a bit how that works. So let's talk about some practical ways or understanding the actual implementation of the particle filter. So there's many things that you have to control that will change the behavior of your and accuracy of your localization. The very obvious one is the number of particles. Now you can imagine if you have 10,000 particles, you would have to simulate these possible range vectors 10,000 times, and each of them will have thousands of rays. So it's a pretty hefty computation. So this number alone is the biggest sort of factor which dictates how much time is utilized in localizing or doing this recursive sort of estimation of the state. Definitely the number of particles plays a big role. There are some ways to reduce the computation. For example, you don't need to simulate, all 1,080 LiDAR measurements from with this raycasting. You could do some downsampling where your angle step or your increment in this fake LiDAR data is maybe 4 times. It's downsampled by a factor of 4 compared to the real LiDAR, right? So you can specify that angle step as well. The range of the LiDAR also influences your particle filter because the longer you can see, the better shot you have about getting these unique correlations right at the very beginning. And since you can see that, we want to there is no reason that if you have 1,000 particles that you are just calculating the weight of one particle and waiting sequentially for going through each one of them. So the setup of the problem is such that it lends itself beautifully to utilization of parallel computing and GPUs in particular, because all of this is very compatible with matrix multiplications at the end of the day. And so this particle filter algorithm can be optimized to run in parallel on GPU, and that will also alleviate some of these computational concerns. So all we really need, to for this to work, or the AMCL or the particle filter package to work, is we have to give it a map file in one of our launch files. So we replace or send the path to the map server, and this map has to be a 2D cost map. And the particle filter algorithm should, in the launch file of the particle filter algorithm, you need to tell where your map is. It will open RViz. You can specify your initial guess, and then it will spawn the filters to figure out or estimate the position of the robot in the map as it moves about. And in the next sort of video, I'm going to show you how this works in the simulator, but this is just a preview of that. So there are many parameters to tune. Number of particles has a minimum and max. We've already discussed this. You may also want to save some computation by saying that I will only trigger a new batch of particles, or I will only trigger this updated estimation once my robot has either traversed a minimum distance or rotated by a minimum angle. And so if you recall, even in Hector Slam, you had similar sort of parameters where there was a problem of how often do you update the map. So it's a similar, analogy to localization. You can control how often these updates happen. You can definitely provide the initial pose of your robot. And not only that, remember how I said that the initial pose is extrapolated into an uncertainty ball, and you are sampling from that ball. You can even provide the variance of how big that region is. If there's some reason to believe that it must be there must be more uncertainty along a certain axis compared to something else, AMCL allows you to specify that to that level of detail. So here's another example. You can see the yellow arrows are nothing but a history of the best particle or the expected position of the robot. And as the robot moves in this world, it actually computes these particles. And I can replay this this video again, so we can take a look at the particles which are also shown. So you see these red arrows as well, which are a bit difficult to see, but these were the guesses, and the yellow is sort of the winning candidate at every time step as this robot was moving. So now if we go back and see this video again, I think it will make more sense than the first time you saw it. So let's just pay attention to what's happening to the pose of the robot. As we zoom in, you can see all these red arrows are particles. There's hundreds of particles, which are guesses, and very, very rapidly, since it's running on a GPU, the green arrow is the best candidate or the best estimate of the robot. The blue is our best guess of the position of the robot based on the IMU data alone. So you can see they are in good correlation with each other. But here you see we were able to localize the robot very well inside a pre-existing map. That was the setting of the problem, using this idea of particle filters with weighted sampling or resampling. So I want to stop here. This is a short video today, or short lecture today. In the next lecture, I'm going to show you firstly how to simulate this in our autonomous racing simulator. I'm going to show you the scripts, and so it's more of a tutorial video over there. And with this, we can claim that we've completed our study of SLAM, which is basically a way to map the environment and also localize yourself within the environment. Why do we care about this as a reminder? Well, firstly, because this is very interesting and it'll allow us to do more interesting things. But in particular, this is important because, as you can see in your previous assignments that you've just submitted, you were mostly limited to reactive approaches of wall following, where you actually didn't care what the map or the world looks like, right? So you have some error that you compute against the wall, and you always maintain some fixed distance from the wall, and that is enough for you to do a loop. But what if I ask you, can you find or trace the fastest race line? Now, you may claim that it is possible to do so because you can change your distance from the wall in a manner that your car will trace the fastest race line. But a better way would be, given a map and given a trajectory that you want to follow in the map, you can utilize SLAM to firstly build the map, and then localization with AMCL or GPU particle filters to localize yourself such that you know whether you are on the race line or not. And that's why this is important in the context of autonomous racing. All right, so I just want to close by pointing you towards a set list of references. I would definitely recommend you to, if you can get access to this book on probabilistic robotics. A lot of this Bayesian filtering techniques and the derivation of those expressions are beautifully described in this book. So I would definitely recommend, if there was one that you have to read from this reading list, it would be the first one. But all others are also, some of them are freely available on the web. So have a, feel free to go over them. And if you have any questions, you can let me or the TAs know on Piazza. I'll be happy to help you out. So with that, I conclude this video, and I'll see you next time when we will take a look at the simulator and how to put together ideas of SLAM and motion planning and sort of a race line tracing together to attempt the next version of advanced algorithms for autonomous racing.